We saw before that light has a dual nature. It has a wave nature and a particle nature. And previously in the interference and diffraction we studied the wave nature of light, whereas today in the photoelectric effect we are going to be studying the particle nature of light. The photoelectric effect phenomenon, it was first observed in 1887 by a German physicist Heinrich Hertz, who shone a high energy beam of light on a metal plate, and he found out that electrons were emitted in that process. But what actually caused the emission of the electrons in the first place? Inside any metal you have electrons that are held inside and occupying a conduction band or an energy level of that metal. And as long as the metal plate is kept at room temperature, therefore the electrons are bound to remain held inside that metal. However, in order for the electrons to be knocked out, to be released from that metal plate, these electrons should be supplied with a minimum amount of energy. And that energy is actually supplied through the means of a beam of light. In other words, through the means of a photon of light. And that energy which is required by the electrons in order to be emitted is called the work function. So what's the work function? The work function is going to be the energy which is needed for the release or for the emission of an electron from a metal plate. And mathematically that work function is given as phi equal to h times mu 0, where h would be Planck's constant, which is a quantity that we need to be determining today. And the mu 0 would be the threshold or the critical frequency of the electrons within that metal. Like I said before, that amount of energy or the work function is actually supplied through the means of a photon of light. So any photon, as we know, it carries energy, and that energy is given as E equal to h times mu, where h would be Planck's constant, and the mu over here would be the frequency of that photon of light. Now the special part about that phenomenon is actually centered around that critical frequency of the electron mu 0, and how mu 0 compares to the frequency of the photon of light. So in that case we can distinguish two different cases. First off, if the frequency of the photon, mu, is actually below the critical frequency mu 0, meaning that that amount of energy is actually below the work function, therefore no electron is going to be released from that metal plate, and therefore the electrons are going to remain held inside. However, if the frequency of the photon of light is now bigger than mu 0, therefore h mu is bigger than h mu 0, therefore electrons are going to be released from that metal, and we are going to refer to these electrons as photoelectrons, and therefore we have an electrical current that is going to be established, and we are going to refer to that electrical current as photocurrent. So depending on the value of mu, depending on the frequency of the photon mu, an electron is going to be either emitted from the metal plate or it's going to remain held inside that metal. Noting that critical frequency mu 0, that threshold frequency, is actually an intrinsic property of each metal, meaning that it varies from one metal to another. So each metal, it has its own critical frequency. So in that case, part of the energy of the photon, which is incident on the metal plate, is actually being transferred into the electron in the form of a work function in order for the electron to be emitted from that metal plate. Now let's suppose that over here we have a certain collector. So over here we have the following collector, which is actually collecting the electrons that are being knocked out by that metal plate. And therefore, like I said before, over here we have now an establishment of a photocurrent between the metal plate and that collector. So in order for the electrons to be moving from the metal plate, or in order for the electrons to be transferred from the metal plate toward that collector, the electrons should have a certain amount of speed. In other words, they should have a certain amount of energy which is none other but a kinetic energy. So in that case, since part of the energy of the photon is being transferred to the electron in the form of a work function in order to knock it out from that metal plate, the remaining part of that energy of the photon is going to be transferred to the electron in the form of a kinetic energy. So over here, that energy is going to be none other but the kinetic energy of the electron in order for the electron to be transmitted from the metal plate toward that collector. So in that case, since we have over here E, which is equal to h mu, is equal to phi mu 0 plus the kinetic energy, therefore the kinetic energy of that electron is going to be none other but h mu minus h mu 0. where h mu over here is going to be none other but the energy of the incident photon. So h mu is going to be none other but the energy of the incident photon. And over here we have h mu 0, which is going to be none other but the energy needed for an electron to leave the metal. Now moving on to the experimental part. Over here we have a vacuum diode. And the vacuum diode, it consists of two electrodes. We have the cathode and the anode, where the cathode is going to be the plate that is going to generate photoelectrons, and the anode in that case is going to be the collector, or it's going to be the plate that is going to collect the electrons that are released from the cathode plate. Now on the other side over here we have a mercury light source, and the spectrum of a mercury light source, it consists of multiple wavelengths, meaning it consists of multiple colors of light, like the yellow, the green, the blue, the violet, and the ultraviolet. And over here in the middle we have a cutoff filter and we have an aperture. What would be the role of each? Starting with the cutoff filter. Over here I said that the mercury light source, the spectrum of the mercury light source, it consists of multiple wavelengths of light. So let's say for example we want to allow only for the yellow light to be incident on that cathode plate and cancelling out all the other colors. Therefore, by using a cutoff filter that has a specific wavelength of that of the yellow light, you would be only allowing for the yellow light to emerge through and be incident on that cathode plate while filtering out all the other colors. Let's say now we want to allow only for the green light to be incident on that cathode plate. Therefore, by using a cutoff filter that has a specific wavelength of that of the green light, you would be filtering out all the other colors and only allowing the green light to emerge and be incident on that cathode plate. Now regarding the aperture is similar to the one that we have seen in the case of diffraction. And that aperture over here, it can come with multiple width. So the role of the aperture in that case would be for light to undergo diffraction and be incident on that cathode plate. So as we can see over here, light which is emerging from that aperture is actually undergoing diffraction and is covering the entire cathode plate. Moreover, that cutoff filter over here, it can be used also as a way to prevent any unwanted heating. So the cutoff filter, it can absorb any unwanted heating and therefore preventing any damage to that vacuum diode over here. Now the target in today's experiment is actually to determine something called the stopping potential. What would be the stopping potential in that case? When you have over here light that is incident on that cathode plate, you are going to have electrons that are going to be knocked out from that cathode plate and directed toward the anode. So over here we have a photocurrent that is going to be established between the cathode and the anode. So since we have a photocurrent, since we have an electrical current established between the cathode and the anode, therefore over here we have a potential difference between the cathode plate and the anode plate. And we need to determine that amount of potential between the cathode and the anode. So each color of light is going to have a certain potential that's going to be specific to it. In order to determine the amount of voltage over here, we are going to be applying a reverse potential, which is called a stopping potential. And in order to apply a reverse potential, we are going to be connecting the diode over here to an external power source. So as we can see over here, the anode is being connected to a negative terminal and the cathode connected to a positive terminal in order to apply a reverse potential. And over here we have an ammeter and we have a voltmeter in order to detect the value of the voltage that we are applying. So over here we have the photocurrent directed from cathode toward the anode. So by applying a reverse electrical current, or in other words by applying a reverse potential, and by observing over here the value that the ammeter is registering, once the ammeter is recording a value of 0 amps, therefore you have actually reached the same amount of the potential difference across the cathode and the anode. Meaning that whenever you keep varying the voltage of that power source over here until you observe a 0 amps on that ammeter, therefore over here you have matched the same amount of the potential difference between the cathode and the anode, and that value would be called the stopping potential. So for example, let's say for the green light, the green which has a certain wavelength, it's going to have a certain potential. In order to determine the potential which corresponds to the green light, therefore you are going to be applying over here a reverse potential in order to counter the potential of that photocurrent. And therefore, once the value which is registered on the ammeter drops to 0, therefore you have matched the same value of the potential between the cathode and the anode. And therefore over here you would be recording V stopping, or simply the stopping potential. That would be for the green light. Then you have to repeat the same thing for the yellow, for blue, for ultraviolet, and for the violet light. So let's say now we want to find the stopping potential of the yellow light. So the yellow light, it has also its own wavelength. Therefore over here you would be removing that cutoff filter, and you would be using a cutoff filter which is specific for the yellow light. And now in that case, the value of the electrical current that you are going to be reading on that ammeter is going to be different than the one of the green light, simply because each color, it has its own stopping potential, it has its own voltage, and therefore it's going to have its own electrical current. The target, like I said, is to find the voltage which corresponds to that of the yellow light. To find it, over here we are going to be varying with the voltage of that power source until the value that we are reading on the ammeter drops to 0. So once the value of the current drops to 0, therefore we have reached the same value of the potential difference between the cathode and the anode, and therefore we would have found in that case the stopping potential of the yellow light. And then you repeat the same thing for blue, for violet, and for ultraviolet. Since over here we are actually applying a stopping potential, we are applying a reverse potential, which is actually hindering the movement of the electrons, of the photoelectrons between the cathode and the anode. Therefore, the work done by that stopping potential is going to be opposing the energy of the photoelectrons. We know that these electrons, these moving electrons, they have a certain kinetic energy, which we have defined it before over here to be Ke equal to the difference between the energy of the incident photon minus the work function. So these electrons over here, they are carrying a certain kinetic energy. In order for these electrons to be completely stopped, therefore the work done by the stopping potential should equal the kinetic energy of these electrons. Therefore, the kinetic energy is going to be equal to the work done by the stopping potential. So like I said, in order to completely stop the movement of the electrons in that case, you have to match their kinetic energy. And in order to match their kinetic energy, meaning that the work done by the stopping potential, by the reverse potential, it should equal that of the kinetic energy of the electrons. Therefore, in that case, we can write down that Ke is equal to the charge of the electron times the stopping potential. And that would be the work done by the stopping potential in order to hinder the movement of the electrons. In that case, the final equation becomes Ke equal to, we have seen before that the kinetic energy is equal to the energy of the photon of light minus the work function. And over here we have defined the kinetic energy to be equal to the work done by the stopping potential. So that entire equation is also equal to E times V stop. Therefore, the equation becomes E times V stop equal to H mu minus H mu 0. Therefore, the stopping potential would be equal to that entire equation divided by the charge of the electron. Therefore, H over E times mu minus H over E times mu 0. And that would be the final expression that we are going to refer to in order to solve our problem today. Let's have a look at the report that we are going to be solving today. As we have seen before, that the mercury light source, the spectrum of the mercury light source consists of multiple wavelengths. So over here we have all the colors of light that are contained in the spectrum of mercury source. And each color of light, it has its own wavelength. But moreover, over here we need to determine the frequency of each color of light. To determine the frequency, we are going to refer to that expression which relates the speed of light and vacuum to the wavelength and to the frequency. So having the wavelength and having the speed of light and vacuum, we can find the frequency of each color of light. Then over here we have the stopping potential, which is determined experimentally in the same manner that I have described it before. However, as we can see over here, for each trial we are using an aperture of a different diameter. Over here we have an aperture of 4 millimeters, another aperture of 2 millimeters, and a third aperture of 8 millimeters. The thing over here is we are showing that the stopping potential for each color of light is going to be independent of the diameter of that aperture. For example, if we look at the blue light, it has a stopping potential of 1.045 volts for an aperture of 4 millimeters. Then by switching to an aperture of 2 millimeters, now the stopping potential of the blue light is at 1.053 volts. So as we can see, these two values are too close, and you have to account over here for any experimental error, for any margin of error. Then for the third aperture, which has a diameter of 8 millimeter, now the stopping potential of the blue light is at 1.081 volts, which is also similar to the previous two stopping potentials. So as we can see over here, the diameter of the aperture, it has no effect on the value of the stopping potential for each color of light. Now regarding the questions below. Over here they are asking you to use linear regression in order to find slope of the stopping potential versus the frequency of the photon of light. So we are finding the slope of V stop versus mu. So the stopping potential versus the frequency of the photon of light. Then after finding that slope, they are asking you to deduce Planck's constant. Like I said at the beginning, the target in today's experiment is to determine a value for Planck's constant. So after finding a value for slope, you are going to find now an expression for slope. So over here we have V stop, which corresponds to the y variable, and mu corresponds to the x variable. Therefore h over e over here is going to correspond to the slope. Then by using that expression, having the value of slope, having the value for the charge of the electron, you can find the Planck's constant experimentally. Then later on they are asking you to find the work function of the cathode material. Like I said before, each metal, it has its own critical frequency. So each electron has its own critical frequency for certain type of metals. So in that case, the cathode plate which we are using today, it's going to have also its own critical frequency and therefore its own work function. To determine the work function, we are going to refer now to the y-intercept. So in that equation we have defined V stop to be y and the mu over here to be x. Therefore that quantity over here is going to be a constant, which is none other but the y-intercept. So by equating the value of the y-intercept with that equation over here, we can find an expression for the work function, which is h mu 0, which is going to be equal to the y-intercept times the charge of the electron. And then you carry on with the rest of the questions. And that would be it for the photoelectric effect.